Howdy, y'all. Dr. Rob Parks here, and welcome to yet another lecture in the series for ASTR 124, Introduction to Observational Techniques. Today, we're going to be talking about quantifying light. More specifically, we're going to be talking about how we actually put a numerical value to the brightness of celestial objects. Now, I want to first start off by saying that yes, there is a dichotomy, as it were, between, or there's a dichotomy, as it were, for the description of light, meaning that you can either look at light as a transverse wave that has a particular wavelength and particular frequency, or you can think of it as a particle, which also has a wave and frequency, or wavelength and frequency to it. To me, which one is reality, which one is more real, is not that an interesting question for me. For me, when I think about light, I think about it simply as a carrier of energy. It moves energy from point A to point B, and depending on the situation and how much math I want to do, I will either characterize it as a wave or I will characterize it as a photon or a particle of light. For this lecture, and for most part moving forward, I will be treating light as a wave, as it is easier to talk about certain concepts in that context. When we talk about CCDs, digital recording devices, I will probably switch over to a photon model, simply because we're dealing with the photoelectric effect. And again, it is easier to conceptualize these things as light as a series of particles. But anyway, let us get to it. I want that one. Actually, let me try this again. No. All right, I will just have to deal with the Google bar at the top. All right. So, quantifying light. First, in order to really have a discussion about what light is, we need to introduce what is known as the electromagnetic spectrum. Now, I'm not going to spend a lot of time going over this. If you want more information, I will post a link to a general information video that I have done on light, which can go into this a little bit more in depth. But effectively, the electromagnetic spectrum is the entirety of all light that is in the universe, in a way. And like I said, we can define light in terms of its characteristic size or wavelength, and we can also define it by its characteristic frequency. Essentially, how many times does the wave oscillate at a particular point every second? The unit for that is hertz or per second. So a light wave that has a frequency of 60 hertz will oscillate at a particular point in space 60 times every second. And so astronomers have divided this huge electromagnetic spectrum into various regimes. The one that is biologically driven is called the visible range, and that, roughly speaking, is between 400 at the blue end and 700 nanometers. Depending on how well your color eyesight is, it might go a little bit smaller than 400. It might extend a little bit larger than 700. The visible spectrum is, as the name would imply, the light that we can see with our eyeballs. For the most part, again, within this lecture series, within this class, I'm going to be talking about applications or essentially procedures or techniques that are used in the visible range, although there is some applicability to other wavelengths, but I'm going to be primarily concentrating on the visible range. Occasionally, I will specifically talk about other wavelength regimes, particularly the radio. Later on, I will just have a lecture just simply on radio astronomy. But anyway, radio waves have long wavelength, small frequency. And then as you increase in wavelength, you have microwaves, Wi-Fi is in there somewhere, you have infrared, then visible, then ultraviolet, X-ray, and gamma ray. These will also come into play, or these distinctions will also come into play when we talk about how we can do observations, or more specifically, where we need to do observations in order to get good data. For example, thankfully, because these things would kill us, the atmosphere blocks out ultraviolet, X-ray, and gamma ray pretty effectively, meaning that if you are interested in looking at something in those regimes, you have to go above the Earth's atmosphere and into space. Now, why would you be interested in looking at those regimes? Because the other thing that is traced here, as I said before, is energy. So radio waves correspond to low energy phenomenon, whereas gamma rays are extremely high or extremely energetic phenomenon. For example, radio is primarily used or can be used as a great tool for tracking the neutral hydrogen in the galaxy, which has a temperature on the order of a few tens of Kelvin, whereas gamma rays are needed in order to probe such energetic things like supernova, but even more energetic like, gamma ray bursts, which we believe are the result of two black holes merging into one and exploding. Hypernova, where two neutron stars collide, is also something that gamma rays will allow us to probe more effectively. So let me first introduce something known as the black body spectrum, or in astronomical terms, we refer to it as the spectral energy distribution. A black body is a theoretical body where it is a perfect absorber emitter, meaning that it emits all of the light that it absorbs at the wavelengths at which it absorbs it. This is a how should I put it, approximation for things like stars. Later, when we really start getting into spectroscopy, I'm going to show that stars are black body-ish. There's a phenomenon known as line blanketing, meaning that because of the absorption of certain elements, light in the bluer end of the spectrum tends to be suppressed, whereas light in the ultraviolet and the infrared is enhanced because the energy has to go somewhere. But regardless, we can use black body spectrum or spectral energy distributions as a tool to understanding how astronomers actually measure light and use it to find very fundamental things about objects such as luminosity, radii, temperatures, so forth. So as you can see here, there are 4 plots based on the temperature of the black body. And really the temperature is what defines the characteristics of a SED, spectral energy distribution. You have at the bottom 3,000 Kelvin, 4,000 Kelvin, 5,000 Kelvin, and 6,000 Kelvin going up. There are a couple of things to note here. One, as it should be obvious, the area under the curve for the 6,000 Kelvin is extremely larger, or much larger, than the area under the curve for the 3,000 Kelvin. The other thing, which the curved dotted line is attempting to illustrate, is that the peak of these curves shifts, the wavelength of the peak of these curves shifts as you go to cooler objects or hotter objects. It shifts to the right if you go to cooler objects, meaning that the most energy produced as a function of wavelength moves towards the redder end of the electromagnetic spectrum for colder objects. It still emits light in other wavelengths, but just not nearly as much. So one of the reasons why we do not glow in the dark as human beings who do have a temperature and in a very kludgy way could be treated as a black body our temperature is, let's see, I want to say around 290 Kelvin, something like that on in your average room. The peak of our black body curve is squarely in the infrared, meaning that you would need specialized equipment in order to see us. Or you would need image enhancing goggles to see us, because we do put out light in the visible range, just not a lot of it. So much, so less so that, again, we cannot see each other in the dark without specialized equipment. Now, how do we quantify this? So that was a diagram showing what the black body curves look like, but from a mathematical perspective, how can we describe that? And we can do that using what is known as the Planck's law, which is listed here, where BVT is the amount of energy being emanated, or being, what's the word I'm looking for? Emitted as a function of frequency. Frequency is designated by the Greek letter nu. Lambda is the designation for wavelength designation for wavelength. So these two equations are effectively describing the same thing, just in different terms, one in terms of wavelength, one in terms of frequency. And so you can see, just to note, the H is the Planck's constant, which you can look up. It's one of the fundamental constants of nature. K is the Boltzmann constant. You can also look that up anywhere. And then C is the speed of light. And so the primary characteristic here, as you can see, not only from frequency or wavelength, is temperature. These curves, these distributions, are really a function of temperature alone. Now, as I was saying before, well, the first thing that should pop out when you look at these distributions is that for a hotter object, the curve is bigger. And what that means is that star is hotter, and so that star is emitting more energy, which hopefully is fairly intuitive. The warmer something is, or hotter something is, the more energy that it is putting out as a function of time. Oh, I should also mention that the Planck's law, the units are listed. They are ergs per second per inverse square centimeters per hertz per steradian. Steradian is a solid angle. So effectively, it's looking at the amount of energy that is produced within a certain beam over a certain time with a certain frequency or wavelength. Oh, actually, I believe there's a typo. Wavelength, the hertz value of the hertz should not be there. It should have been converted. I think I mistakenly forgot to delete that. But to note here, you might be wondering, what is an erg? Well, an erg is a unit of measure for energy in the CGS unit system. If you have taken physics, you're more than likely familiar with the MKS system, which is kilogram or meters, kilograms, and seconds. So those are the base fundamental units of distance, weight, and time. For reasons that I've never quite understood, astronomers who study the largest structures in the universe have decided to use a different system, CGS, where it's now centimeters, grams, and seconds. And so you will see different units in that sense. So again, that's why there's an erg and why you have centimeters per second rather than meters per second, just in case you are curious. Now, one of the most fundamental properties of a star, or really any astronomical object, is how much energy is it producing in toto per second. And we refer to that as luminosity. This is an intrinsic quality. It is not dependent on where you see it, how far you see it, in what way you see it. Luminosity is an intrinsic part of the object due to physical processes. And effectively, you can get there using by integrating the Planck's law over the entire surface, over all wavelengths or frequency. In this case, I have listed it in terms of wavelengths, but ultimately it doesn't really matter. You finally get to the endpoint, which is the luminosity is equal to 4 pi r squared sigma t to the fourth, and that is known as the Stefan-Boltzmann law, where sigma is the Stefan-Boltzmann constant. Now, again, I'm not going to get too far into that rabbit hole, but temperature is not a simple thing to describe in astronomy. There are a couple of different ways you can describe temperature. You can describe it as a brightness temperature. You can describe it as the Rosalind mean temperature or the effective temperature, and so forth and so on. It really depends on where and what you are actually measuring. In this case, the Stefan-Boltzmann law is measuring what is known as the effective temperature. And what that means is that you can take that as the temperature of the gas on the surface of the object. And so for a star, that is the photosphere. So for our sun, that is 5,880 Kelvin. So that is the effective temperature of the object. Obviously, if you go deeper within the star, it gets much, much warmer, to the point that if you're at the core, you're somewhere in between, somewhere around 10 to 15 million Kelvin. But we use that as a characteristic temperature. Or as the radius, again, the units are in centimeters. You can break this law up into essentially two sections. You have pi r squared, which is the surface area of the star, and then you have sigma t to the fourth, which is defined as the stellar flux. That is the flux coming out of any particular area on the surface. And so with this is one of the workhorse methods that astronomers use in order to determine stellar radii. Oh, I should take a step back and say that the Stefan-Boltzmann law is derived with the assumption that you are dealing with a spherical object, which for most stars, that is a reasonable assumption to make. There are exceptions, but for the most part, that is a reasonable assumption to make. At least it's a very good starting point. But anyway, so this equation shows the relationship between luminosity, the radius, and temperature. And you notice that while it is a relationship to radius squared, so if you double the radii of a star, the luminosity of that star becomes 4 times. But it is a steeper function of temperature, which is one of the reasons why that there was such a dramatic rise in that curve when you go from 3,000 to 6,000. You are doubling it, which means that you now have 16 times the luminosity, assuming you're talking about stars of the same radii. So what astronomers can do is, by using certain techniques, specifically spectroscopy, although you can do it photometrically, you can independently determine the luminosity of a star and its temperature, and from that you can work out its radius. There are other techniques, but like I said, that's pretty much the workhorse method. Let me take myself off this. The other relationship that is useful to know with this is Wien's law, which you can derive by looking at the inflection point of the SED. Basically, take the derivative of the Planck's law and set it equal to 0, and then solve for lambda. Again, you can do this in terms of frequency, but it's almost exclusively shown as a wavelength relationship, where you have the max wavelength, the peak of the stellar spectral energy distribution, the SED. The peak of the SED is simply 2.9 times 10 to the 6 over the effective temperature, where in this case, the units are in nanometers per Kelvin. So if you can properly sample the SED such that you can measure that inflection point, that lambda max, then you now know the effective temperature of the star, which is one of the components you need in order to determine the intrinsic luminosity of it. Now, as again, from the easiest, or most, not easiest, the best method, the method that you are going to have more precise, more accurate value, I should say, is spectroscopically. And again, we'll get into spectroscopy later. For the most part in this course, I'm going to be concentrating on photometry, the study of brightness. What you have here is the spectral energy distribution for a particular star. I think it's TPYX, TPYX, which I think is a southern hemisphere star. Anyway, what you have are a number of observations, another of photometric observations in particular wavelengths, which are now sampling that SED. The SED that you see there is a modeled SED based on the physical characteristics of the star. A star with an effective temperature of 6,500, a surface gravity, a log surface gravity of 4, and a radii of 2.25 solar radii. Here you can kind of see the, it looks a little weird or a little different from the other one because the y-axis is now logarithmic rather than linear. But you can see kind of what I was talking about in terms of that line blanketing effect. You have these absorption lines on in this area. These are the basically sharp decreases in luminosity. These are caused by absorption by particular elements within the atmosphere of the star. And then what that does is, again, that depresses the amount of energy being released in the blue, and it has to go somewhere. So that energy is typically released in the red. This requires multi-wavelength photometry, and the more the better, meaning that you would like to have photometry not just in the visible part of the spectrum, but also in the ultraviolet, or excuse me, in the infrared, ultraviolet if you can get it, and possibly even the radio. So I talked about getting multi-wavelength observations such as these. Now, in order to do that, or do that effectively, you need to use filter sets. So the light that is coming into the telescope is multi-wavelength. It is basically all of the wavelengths that the physical object is emitting to the Earth. For the sun, again, it's or for this, for example, this is the amount of energy as a function of wavelength. A telescope will receive all of this. Depending on the type of the telescope, it's only going to sample certain wavelength regimes or bands. So, for instance, our telescope is in the optical band or the visible band from, say, 400 to 700 nanometers. And that's primarily what I'm going to be concentrating on. In order to study that a little bit more in depth, we segment it even further by putting pieces of glass in between the incoming light coming in from the telescope and the detector. In modern sense, the CCD or CMOS chip. And what this allows us to do is allow us to pick out certain wavelengths within the optical spectrum. So the most common, for at least for the optical spectrum, is what is known as a Johnson-Cousins filter system. And you can see that on the upper side where it's U, B, V, R, and I. And those curves indicate how much light is allowed to pass through that piece of glass and actually get detected by the CCD camera. So, for example, the U stands for ultraviolet. It's in the really close ultraviolet part of the spectrum. You really couldn't get a tan from this light, but that's the name we want to call it. So it will only allow light in that small wavelength regime. So here it's roughly from like 3,000 angstroms or 300 nanometers to 400 nanometers. And the amount of light that it allows to go through is indicated by the curve, which is very well characterized. So we know how much light in that part of the spectrum is being allowed to pass through. Similarly for B, which is blue, V, which is visible, but basically green, despite the color of yellow up there. Then you got red, and then you got infrared. But there are a number of other filter systems that are being used. And this is very important to know when we are taking archival data or when we are taking data from other sources, from HST, Hubble, from the Hipparcos Tycho mission, so forth and so on, because they use a different filter system. So, for example, the Tycho system, if you look in Sinbad and it's a Tycho object, it's going to list B and V magnitudes. The thing to note is that those magnitudes are not in the Johnson system. So you cannot compare them directly to observations, say, we take at our telescope. You have to transform them. You have to make a correction in order to properly compare apples to apples. There are two types of filter sets. There are what are known as broadband filter sets. These are like the Johnson Cousins, the Sloan Digital Sky Survey, which is what is used primarily on Aladdin, which we talked about last time. And these bands are typically in the hundreds, possibly 1,000 of nanometers in terms of what we call passband. How much wavelength coverage does it allow through? And then you have narrowband narrowband filter systems or filters. Strongram is the most common that I'm aware of. That is a complete filter set. H alpha is a filter which specifically looks at the H alpha emission line of hydrogen. And then O3 is the emission line from doubly ionized oxygen, or at least one of the lines from doubly ionized oxygen. These are typically used for studying specifics in nebular activity or determining the temperatures of nebula within the O3. H alpha is very useful if you are interested in accretion processes, where a mass from a disk, for example, is being dumped onto a star. You're going to get a lot of H alpha emissions. So if you're interested in that process specifically, using a narrowband filter is advantageous. Now, one of the reasons why we would want to use one system to the other, particularly a broadband to a narrowband, the Strongram filter was designed for a specific purpose. And there is a phenomenon which is known as the Lyman jump. And so this is where a star goes from a region going from short wavelength to long wavelength, so high energy to low energy. In the ultraviolet, the opacity of the star, or how easy is it for the light to get through the stellar material, is very high, or at least higher in respect to longer wavelengths. And so what you can see here is when you go from short to long wavelengths, around the 350 nanometer line or wavelength, or 3,500 angstrom, you have a rapid increase in luminosity, or a rapid increase in flux. And the height of that jump, the amount that it increases, here in this case, it's going from 0.4 to 1 relative flux. The height of that is a direct measure of temperature. It is from a photometric standpoint, it is a very imprecise measure of how hot a star is. And so if you look at Strongram U and Strongram V, the red filter and the V filter, you can get an estimate of how bright the object is prior to the jump and how bright the object is after the jump. And if you compare those two brightnesses, then you can get like I said, a fairly precise measure of the temperature of this particular star. We'll get into color index in a moment. So before we go any further, we have to talk about the magnitude scale. I've been talking generally about the brightnesses of things, the fluxes of things. So what do we actually measure at our telescope, or how do we quantify it at our telescope? Well, we have two gentlemen to thank for this. On the right, you see I guess an engraving of the Greek Hipparchus. He was the one who developed the magnitude system. What he did was he waited until dusk. The first stars that appeared in the night sky, he labeled as first magnitude. At some point, he cut that off, and the next groupings of stars they saw were second magnitude, all the way down to sixth. So the faintest stars that he could perceive in ancient Greece in the middle of a field, that is what he designated in sixth magnitude. And because we have kept the system, sixth magnitude is, generally speaking, the limit of human vision. Again, you can get a little fainter depending on how good your eyesight is. The distinguished gentleman on the left is N.R. Pogson. He's a British mathematician who in the 1880s, finally decided to throw math at the problem. The magnitude system, up until this point, believe it or not, was very much subjective, and there were different magnitude systems being used among astronomers, and Pogson decided, you know what, we need a standardized system. And so he threw some math at it, and what he did was he made a certain distinction. And that distinction is that the difference in brightness between a first magnitude star and a sixth magnitude star, he defined as 100. So a first magnitude star is 100 times brighter than a sixth magnitude star. And as it happens, there is a biological motivation for this. I'm not sure if he's aware of this, but there is one, in the sense that the way that our eyes effectively collect and measure, brains included, measure light is logarithmic. We see changes in brightness as a logarithmic scale as opposed to a linear one. Before we go, I want to get into the terminology of the magnitude system. So to start off with, the coefficient or variable little m sub lambda or some lambda is what is known as the apparent magnitude at that particular wavelength. So it's what we call monochromatic, a single wavelength, a single color. That is the apparent magnitude because that is the magnitude or brightness as it appears to us as an observer on the Earth. Capital M sub lambda is the absolute magnitude of that object at that particular wavelength, and it is defined as the apparent magnitude as if you are observing that object from 10 parsecs. It's a way to make it more of an absolute measure as opposed to a relative measure, because apparent magnitude is dependent on two things. One, the intrinsic brightness of an object, but also on the distance away from it. You can imagine you have a light, a candle and a flood lamp. Obviously, the intrinsic brightness of the flood lamp is far greater than the brightness of the candle. And so, but you can also imagine that if you push the flood lamp far enough back, the apparent brightness of those two objects is going to be the same. So in order to sort of mitigate that, we have defined absolute magnitude as the magnitude at the apparent magnitude at a set distance. Because of this, we can now, and because of the system that I'm about to get into, we can now throw numbers at it. We can actually assign values to brightness. And unfortunately, it's a bit confusing, particularly when, at least for me, when we start getting into color indices, it's a bit counterintuitive because effectively a lower value of magnitude indicates a higher brightness. So the following are the apparent brightnesses of objects. For the sun, the apparent brightness of the sun is negative 26.76. Incredibly bright. Again, we're talking about a logarithmic system. The brightness difference between 6 and 1 is 100 times. So you can imagine, well, you don't have to imagine, you just go outside and see just how friggin' bright the sun is. The brightest star in the night sky, Sirius, is actually negative 1.6. Polaris, the North Star, isn't all that spectacular. It has a magnitude of around 2. 51 Peg, which is the host of the first exosolar planet around a sun-like star, is actually barely visible in a very good sky, and that is 5.49. Whereas M87, an elliptical galaxy, has an integrated magnitude of 8.6. We'll get into integrated magnitudes later. Again, limit of human vision is roughly around 6 magnitude. And then finally, you have what is known as the bolometric magnitude. Bolometric magnitude is the whole shebang. So before I was talking about wavelength or magnitudes at particular wavelengths, bolometric magnitude is the brightness of the object over all wavelengths. So again, magnitude scale as defined by Pogson states that the flux of one star relative to the flux of a second star is defined as the fifth root of 100 raised to the power of the magnitude of first star minus the magnitude of the second. And so you can rewrite that in the following way. M2 minus M1 equals negative 2.5 log of F2 over F1. F is flux in this case, but from a functional standpoint, that value, so long as you are consistent in the way you define your brightness, you can do so either through flux units, ergs per second, or luminosity units, or even counts in a CCD, how many photons you actually detect at your using your instruments. So long as you're comparing apples to apples, the specific entity or a specific quality or quantity that you are measuring, luminosity, flux, counts, or whatever, it doesn't matter so long as they're both the same. There's a generalized form of this, and this is m lambda equals negative 0.5 times log of f lambda plus c lambda. Now, this is a way to determine the absolute flux of an object, or the absolute, or the actual apparent magnitude, if you are actually seeing it in space. C is a 0 point. That 0 point changes depending on what filter system you're using, and is generally speaking determined empirically. For the purposes of this class, we're really only going to be dealing with the difference equation, where we're comparing one star to the other. Absolute photometry to determine those 0 points is a bear, and honestly could not be done at this site because of the fact that because of light pollution, our sky is not evenly illuminated, which is a necessity. So what if I wanted to get to luminosity based on the brightnesses of things? There is a way to do it photometrically. And so we want to change the counts that we measure at the telescope to a intrinsic value of luminosity. And so if you go back to that definition of the absolute magnitude, you can get to something known as the distance equation. Little m, parent magnitude at a particular wavelength, minus the absolute magnitude at that wavelength, that is known as the distance modulus, is equal to 5 times the logarithm of the distance in parsecs divided by 10. Or you can write it in a simpler form where the distance modulus is 5 times log distance in parsecs minus 5. So in this case, the distance to the object needs to be known. This is a way that you can determine the distance to an object, assuming that you can get the absolute magnitude some other way, some other independent way. There's another thing to consider, that the universe is dusty, that there is a good amount or fair amount of particulate matter, mostly silicate, floating around in interstellar space. And depending on where you look, the amount of light or the amount of dust changes. And this has been fairly well mapped out within our own galaxy. We don't tend to worry too much about intergalactic dust. We do not expect there to be an appreciable amount. The main contributor to what happens when you have dust is within the galaxy. And again, it depends on where you look. If you look within the disk of the galaxy, you're going to see more extinction due to dust. If you look within star-forming regions where there is a much more concentrated region of dust, you're also going to have this effect. Now, I mentioned that this word extinction. Again, I'm not going to get too far into it here, but what dust does is that it attenuates the light. Basically, it will scatter the light coming from the object out of our line of sight, so it never reaches our telescope. So objects appear dimmer regardless of wavelength. Less so in the infrared than in the shorter wavelengths and the longer ones. It is a wavelength dependent phenomenon, hence why it's a sub lambda. The other thing that it does is that it makes things look redder than they actually are. But if you want to be proper about the whole thing, then the distance modulus that is observed is equal to the distance modulus intrinsic, that's actually there, minus that absorption coefficient. So Once you've gotten the absolute magnitude of the star, so you would need to know what the distance of the object is, you would need to know the absorption coefficient, or at least have a very good rationalization as to why you did not include that in your calculations. You can get the absolute magnitude. Now, so you can get the bolometric magnitude, bolometric absolute magnitude, using this simple equation. The bolometric magnitude is equal to the magnitude at a particular wavelength plus a bolometric correction. Again, this is generally speaking determined empirically, is that you know what the energy is for a particular type of star. You know how much energy you're getting, and say the V band of the optical, and so you can compare those two particular values, and then you can use a correction to get that, convert from one to the other. So hopefully it's obvious that the amount of light that you detect, the flux that you get from the star at a particular wavelength or band, the visible band, is going to be much smaller than the overall light that you can get. So the magnitude value is going to be in a particular wavelength is going to be dimmer, so it's going to be much lower as a value than the bolometric magnitude, which is why you would need to add that bolometric correction. And then finally, you can go back to the magnitude equation, and you can set it up such that the bolometric magnitude of the star minus the bolometric magnitude of the sun is equal to negative 2.5 log of the luminosity of the star divided by the luminosity of the sun. Now, the sun, as you might expect, is very well studied, so we know that the absolute magnitude of the sun is 4.74. So if the sun were out in the sky, it would not be a very superfluous object or a superlative object. Basically, if you were 10 parsecs away from it, it would be on the low end of the visible range in terms of being able to see it. So if the sun were, for example, 10 parsecs away from the Earth, we would not be able to see it with our eye here on our campus. Our limiting magnitude on campus is at best of times around fourth magnitude, worst of times is around 3.5. The luminosity of the sun, as you might well expect, is extremely well known. It is 3.8 times 10 to the 33rd ergs per second. You'll have to forgive me as much as I go on about errors. I have not included error bars here, but trust me, it is a pretty precise value. Whoops. So now you can solve that equation. I leave it to you to rearrange that equation, and you can solve for lambda star or L star, the luminosity of the star in question. Now let's talk about a color index. Now, color index for Johnson-Cousin, common ones are U minus V, B, B minus V, V minus R. Again, this is a rough estimate of temperature. So what you're doing is you're comparing the amount of energy or the flux that you capture in a blue waveband in comparison to a redder waveband. Never the other way around. So U is bluer than B, B is bluer than V, V is bluer than R. So you would take you would determine the magnitude of an object, of a star, in the U filter. You would determine the magnitude of the star in the B filter, and you would then literally subtract them, and that gives you your color index. Again, because of the inverted nature of the magnitude scale, the smaller the index, the bluer and hotter the object is. So for example, if you have a star with a B minus V of -1, that is hotter than a B minus V of 3. It's also considerably bluer in color than B minus V. This is a very useful tool if say you wanted to study red stars exclusively, and you wanted to make a target list using a catalog from Vizier. You wanted to use Vizier to create a target list of just simply cold stars that have temperatures roughly between 3,000 to 5,000 Kelvin. That has a particular color index range, which you can then put into Vizier, and it will spit out only those stars within that range. And so you would say you wanted to look at these stars, you would look at, B minus V between 2 and 3, and that would very much narrow down your target list to cool red objects. And you can see that from the magnitude equation. If the flux from B is over V is greater than 1, then the difference in magnitudes is less than 0, is negative. So, speaking of cool stars, brings us finally to spectral typing. Again, we'll revisit this when we talk about spectroscopy, but I just wanted to throw it out here. You can see on the right that you have the thing I want to concentrate on right now is the surface temperature, the effective temperature of the star. Ranges from 25,000 to 3,000 on this diagram moving to the right, but under it you can see color index. So I suppose I drastically overestimated the color index for these red stars. So if you wanted to look at, say, 5,000 to 3,000, you're probably going to want to constrain yourself to a B minus V of like 1 to 1.5. So this is again a very crude estimate of the surface temperature of stars. But let's go to the left. So there, in the early 1900s, a group of women known as computers took the data that the strong, robust Harvard men took, and they came up with a system for trying to figure out a physical rationale or physical classification system for the spectra that they were seeing, essentially the change in the change in brightness as a function of wavelength. This is one way of showing it. Before, I was showing you plots where the increase in brightness is a line plot as a function of wavelength. Here, we're looking at what you would actually get at the telescope, per se, where the height of the curve is the relative brightness of the spectrum. Those dark vertical lines, those correspond to those sharp dips in intensity. And so when the first attempt to do this was extremely complicated, Annie Jump Cannon noticed something. And she noticed that if you look at these stars, in terms of the brightness or the strength of their hydrogen emission or hydrogen absorption lines, there follows a nice ordered pattern where you start off with these stars that are very blue, have a brightness in blue. The hydrogen lines are fairly weak, but as you get to stars that are redder in color, the peak of the SED moves to the right. The lines become greater in strength, and then it decreases as you go down. And so that's why the letters are as they are, because the initial was simply based on the strength of the lines. So an A star had the most prominent lines, whereas a Z star had almost no hydrogen emission absorption lines in it at all, or at least none that could be detected. Here, what Cannon noticed was that this is actually, particularly if you look at, again, the brightness of the spectra, where the brightest point in the spectra is, it's a nice smooth shift from blue to red, which means in this ordering, you have not a characterization of just simply how strong the lines are from strong to weak, but actually a function of temperature, which is much more physically meaningful for determining properties of stars or analyzing stars. And so it goes from O-type stars through B to A to F, G, K, so forth. Again, if you want to know more about why the hydrogen lines act this way, see that video in the description for, actually it's a different video. I will put another video in there talking about radiation spectra, and it has to do with, well, the temperature of the stars and how hydrogen absorption lines are created. And so that gives you the spectral type. Then often you will see what is known as the luminosity class. Luminosity class is a proxy for age, effectively, stage of evolution. Again, not quite, I guess, simply because one is brighter than 5. That is the ordering of things. Most stars are what we call main sequence stars. They're burning hydrogen and helium in their cores. And that is given the designation of Roman numeral 5, or Roman numeral 5 or V. As you get to more evolved stages where the star becomes bigger and more luminous, when it is transitioning from burning hydrogen to burning helium in its core to carbon, so forth, luminosities go up. So generally speaking, the ones that I generally deal with are luminosity classes of 5, which is main sequence, luminosity class of 3, which are giants, where you have hydrogen burning in a shell around a inert helium core. And then you have supergiants, which are funky objects that, well, their internal chemistry can be different depending on what the current surface temperature is. So 1 is supergiants, 3 are giants, 5 is main sequence, and then you have intermediate stages. What those intermediate stages are is beyond the scope of this course. I mentioned before that the first spectral typing was complicated. Well, while Canon made it simpler, we have complicated the crap out of it since then. But for our sun, for example, the MK type, which is the combination of the spectral type and luminosity class, is G25. So you can see that on G2, as you can see, the smaller the number, the hotter the object within that class. So a G2 star would fall somewhere around here. So you can see that it is around 5,800 Kelvin. If you scroll up, that means that the sun is approximately here on this diagram known as the Hertzsprung-Russell diagram, and is on the main sequence. All right. And that is all I have for you today. As always, I hope you found it informative and hopefully a little bit entertaining. So next time, we're going to be talking about my favoriteest thing in astronomy, because I loves me some toys, telescopes. I will be talking about different optical designs that have been used in the past and which optical designs for telescopes are now effectively the research standard. So that being said, I will sign off. Hope you all have a good day and return for the next lecture. Clear skies. Peace out and clear skies.